tutorial that are listed as attendees rather than panelists. If you would like to participate, ask questions. If you think there is a chance you might like to participate and ask questions, then please raise your Zoom hands, and we will promote you to a panelist, so you can just unmute yourself and ask questions during the talk. I think it worked well so far, and we might as well continue with that. And yes, and yeah, if people feel comfortable, I think Rachel would love to see your facial expressions as she is giving the talk, so feel free to turn on your video. And with that, let's move on to the second part, the second part of this tutorial by Rachel, who really, I think for you is a very, it's a culmination of a very long journey of trying to base I/O on multilinear maps.
Indeed, yes, struggle with them a lot, but happy ending in the end. So let me talk about the second part of this tutorial on I/O from our founded assumptions. Okay, so definitely questions are very much welcome. I would love to interact with you during the talk. So let me start with highlighting that what is the difficulty that we have in constructing I/O. So as Yao has excellently summarized, basically what we want is a way to encode this function. And then this encoding should allow us to pick any input of we like and evaluate it. And at the end of it, get the output in the clear. So there are two challenges in this task. One is that this evaluation of input X has arbitrarily high degree. If I'm considering a general circuit, if F is implemented by a general circuit of polynomial depth, the degree could be exponential. And the second difficulty part is that we are not satisfied with getting the output in any form of encoding. We literally want the output in the clear. If we think about it and search in cryptographic assumptions or things that we know how to do, and things that resemble this form, and the only thing that we have is bilinear maps. And they will allow us to encode some secret values, and then you can evaluate any degree 2 polynomial on it, and you can actually extract the output of this polynomial in the clear if the output values are small. And if we think about it, that's literally the only thing that we have that resembles this, the task that we have at hand. And therefore, there is sort of like a huge gap between the degree that we can evaluate and the degree that we want to evaluate. Unfortunately, that as Yao quickly summarized, that prior works showed that if we have a very simple pseudorandom generator that can be computed using degree 2 polynomials, we call them degree 2 PRGs, then we can evaluate it inside the bilinear map in a secure way. Then they showed that prior showed that with lots of other effort and lots of cryptographic techniques, we will be able to bridge this gap. The issue is that we don't have degree 2 PRGs. We don't have sound candidates. The best we have, some more reasonable candidates we have degree 3. But if you want to use them, then we will have to corresponding have a trilinear map, which we again don't have. So the ideas in the more recent works is not just in the GLS, but already has been alluded to in prior works, is to use a new notion, which is a degree 2.5 PRGs, and matchingly try to evaluate the degree 2.5 computation using bilinear map. Then we can again use a prior technique to get to I/O. So what is this degree 2.5 computation? As Amit mentioned, is that it's a computation that its input, you can think about it as a two-array function, that the input contains a public input and a secret input. And we allow constant degree on the public input and only degree 2 in the secret input. And this is in general what we call as a degree 2.5 computation. And indeed, we show that actually when I say we doesn't necessarily mean JLS, actually we means as a community, because a lot of techniques were developed by prior works. And we as a community know how to evaluate such computation using bilinear map through this concept called partially hiding functional encryption. And the degree 2.5 PRG has the formal name of structure seed PRG. And combining these two, we can get IO. So this is the leads to the template of this second part of the tutorial, that using bilinear map, we have partially hiding functional encryption. And we can implement this degree 2.5 structure seed PRG using LPN over larger fields and PRG in NC0. And we'll need one more additional tool, which is homomorphic encryption for very simple NC0 functions implemented from LWE. Putting these three things together, we will get functional encryption for NC0. And this is the semi-succinct functional encryption for NC0 that Yao was talking about. And from there, we can bootstrap to FE for polynomial size circuits. And that was shown to be equivalent to IO with a sub-exponential security loss. Okay. So the focus of this part is to show you how to use those intermediate objects to get to functional encryption for NC0. And then Ayush is going to show you how to build structure seed PRG. Okay. So I am not going to throw at you the definition of all those intermediate objects all at once. Rather, I will try to develop ideas step by step and introduce those objects along the way. So hopefully it's clear that what's the purpose of each of the objects. And to start, I will first define functional encryption and homomorphic encryption quickly. And by contrasting those two primitives, we'll get initial ideas for how to approach functional encryption. And then later on, I will introduce these other objects. All right. So homomorphic encryption, here we look at the secret key version. And what it allows us to do is that we can encrypt an input using, since we consider secret key, using both the master public key. You can think about the master public key just as the public parameters and the secret key. And sometimes I will denote this ciphertext with this parenthesis of X, indicating that the encrypted input is X. And I will use the subscript S to indicate what is the secret key involved in this ciphertext. Sometimes I may not append the parenthesis of X and the little s in the subscript. So this is just a convenient notation for me. And the magic of homomorphic encryption is that given any function, we can actually turn a ciphertext of an input X into a ciphertext of the output f of X. This is formally captured as the homomorphic evaluation procedure, which makes use of only the master public key, the function, and the ciphertext, and have no knowledge about the secret key whatsoever. And when we decrypt this output ciphertext resulted from the homomorphic evaluation procedure, what we get is f of X, the output. And the security guarantee is just like a vanilla semantic secure encryption scheme, that it says without knowledge about the secret key, which should be as here, the ciphertext really reveals no information about the input. So even if one can homomorphically evaluate arbitrary functions, everything still sits inside the encryption. Both the input and the output, everything remains hidden. And this is formalized through indistinguishability, where we require ciphertext of arbitrary inputs to remain indistinguishable. The functional encryption is also enabling computation over encrypted inputs. However, differently, that it will allow the evaluator to obtain the output in the clear. To obtain the output in the clear, the evaluator needs additional help. And in particular, that it needs to obtain what we call as a partial decryption key or functional key, which needs to be generated using the master secret key. And the magic is that decryption using this partial decryption key does not give you the encrypted input as is, but rather give you the output of the function evaluated on the encrypted input. Now the security property is that given a secret key, the only information that is revealed should be the function and the output of the function alone. And all other information about the input beyond what can be inferred by the output should remain hidden. And this in the indistinguishability language requires that for any input that yield the same output with respect to the function should have ciphertext that are indistinguishable, even when we give away this partial secret key for decrypting.
Rachel, I always also used to, when I describe functional encryption, use the term crippled key, but then I thought maybe it's not a nice term, and I don't know if anyone has found like a nicer term. I don't know if hobbled key, is there any nicer term?
We call it functional key.
Yeah, functional key.
That doesn't immediately convey the fact that it's less than, that it's restricted.
Yeah, maybe
challenged
partial.
Key. Challenged.
Challenge key, challenge key, okay. Functionally challenged, maybe. Okay, sorry for the interruption.
No, that's a very good question. Yeah, we should have better names. Okay.
Function only key or something like that.
Yeah, so if we come up with some, I would love to use it. So as Yao has already mentioned, functional encryption turns out to be extremely powerful, so powerful that functional encryption for just computing NC0 circuit functions is already implying IO if we assume LWE and the PRG in NC0. And here we require the efficiency requirement on this functional encryption is that we just need the ciphertext size to be linear. It could depend on, obviously, the ciphertext will have to depend on the length of the input. We will also allow it to depend on the length of the output of the function. And just that the dependency is sublinear. We want the ciphertext to be just slightly shorter than the output of the function. And here I'm using this slightly weird notation, big O of lambda, which means that I will ignore all constant factors, but also all polynomial factors in the security parameter. All right, so now our goal is to just realize this functional encryption for NC0 with sublinearly compact ciphertext. And when we think about these two primitives, we put them side by side, functional encryption and homomorphic encryption, they definitely share the aspect that they allow computation over the encrypted input. The only difference is that homomorphic encryption, everything remains hidden if the evaluator has no idea about the secret key. And with the secret key, the almighty secret key, then all information is revealed. So this has this like classical cryptography guarantee of 0 or 1, right? Either you get all information or you get no information at all, and there's nowhere in between. And in functional and for this type of security guarantee, we actually are pretty good at it. And indeed that from learning with errors, we can get homomorphic encryption for all polynomial size functions. However, we are pretty bad at implementing the other type of guarantee, which is about revealing part of the information and hiding the rest. And that's exactly the goal of functional encryption. They want to be able to have this crypto key or partial key or functional key such that reveals the outputs and hide, yet everything else is hidden. So this kind of a half information reveal is what is difficult. And essentially the best we know is to use bilinear pairing groups to get functional encryption for computing degree 2 polynomial in ZP. Okay? And so there's a huge gap in what we can achieve, what we can handle when it comes to these two different primitives, even though that at a high level, they share a lot of similarity. So then the rationale for us towards constructing functional encryption really stems from this comparison. And we observe that if we have a way to decrypt the homomorphic encryption output ciphertext in a secure way that reveals only the output but nothing else, then that's essentially functional encryption. But how can we decrypt in a secure way that reveals only the output but nothing else? Well, that's paradoxical, right? That's exactly what functional encryption allows you to do. So then the hope is that perhaps doing decryption is just simpler then at least we achieve kind of bootstrapping in terms of functionality that use a simpler FE to get a more complex FE. So this is the initial idea, that towards constructing a functional encryption scheme for NC0, we're going to actually just use a homomorphic encryption scheme to encrypt the input, use a secret key that is sampled fresh at random at each time we generate a functional encryption ciphertext. And then we're going to use hopefully a simpler functional encryption scheme for exactly the decryption task, meaning that we hope that the secret key and the ciphertext, when we decrypt, it will reveal exactly the output of the function on X. So let's start with developing this idea by just coming up some version of this function H and some encrypted input that will achieve this goal. The most straightforward way to do it is to let the function H get input, which is a homomorphic ciphertext itself together with the secret key. Then the function H shall first do the homomorphic evaluation procedure to get a ciphertext encrypting the output f of x. Then since it also has the secret key of the HE scheme, then you just need to decrypt, right? Decrypt the output ciphertext, and that gives exactly y. So if this FE bar, this scheme used for FHE decryption, is indeed a secure one, then its security guarantee directly guarantees that only the output y is revealed, and all other information, in particular the secret key of the homomorphic encryption, remains hidden, and then the homomorphic encryption will hide the input x. Okay, the problem is that we're using a functional encryption scheme to implement a functional encryption scheme, so there better be something to gain. And again, we hope for was that this function H that needs to be evaluated should be simple, should be in particular simpler than function f. However, this is absolutely not the case, because a homomorphic evaluation of function f cannot be simpler than function f itself. And furthermore, the decryption algorithm of any encryption scheme that is semantically secure cannot be too simple, right? For example, it cannot be linear. In fact, it cannot have constant degree. It cannot have a small locality, so on. So what are we doing? Turns out that both of those difficulties can actually be handled if we plug in good tools. In particular, we will use a homomorphic encryption scheme where the decryption is almost linear, but not exactly linear. And the second is that if we observe the structure of this computation in H, it has two phases of computation. And the first phase of homomorphic evaluation actually operates completely on public information. It operates on F and it operates on HCT. Both of them are public, there's no need to hide them. On the other hand, that what are secret and needs to be hidden is exactly the homomorphic ciphertext secret key, and the decryption procedure, the computation of the decryption needs to be hidden. So the rationale is that shouldn't we only count those complexity on secret inputs? You know, computation on public information, who cares? And indeed, this can be realized using this tool called partially hiding functional encryption. So next, let me introduce those two tools, and then we'll come back to instantiate this scheme. All right. So a partially hiding functional encryption is exactly meant for evaluating those type of functions that have two inputs. And the one part, the first part of the input is public, and we do not care about hiding. And the second part of the input is what we care about hiding. And the syntax of this scheme is basically the same as the syntax of a normal functional encryption. Then when we obtain a secret key for a partial key for function H, decryption reveals H evaluated on both parts of the input. However, security says that given the secret key, only the output of the function and the public input is revealed. We don't care about hiding the public input. And I'm going to use a slightly different language, which is a simulation language, to formalize this security intuition, that we require that Given the master public key, the secret key for function H, and the ciphertext, these three things can be simulated by a simulator who has only the output and the public input A. Okay, so this is just a slightly different way to formalize this security. We can also equivalently formalize it using distinguishability definition, and these two notions are actually equivalent.
So Rachel, is the way to think about it that you are relaxing the security requirement in a sense that saying you're allowing to leak A, and that enables you to use a function H that are more complicated in their A part than would have been otherwise?
That's exactly what the intention is. And indeed, we show that, well, I'm always confused. When I say we, I mean the community. The community shows that we can implement.
That's the scholarly we. The scholarly we is, yes, you and the listeners and the community at large.
Exactly, yeah. We show that using bilinear maps, we can actually have partially hiding functional encryption for degree 2.5 polynomials. And those polynomials can be written as a quadratic polynomial over the secret part of the input. And the coefficient on those quadratic monomials depends on the public input A, and this dependency could have constant degree. So this form of polynomial H, we call them degree 2.5. More formally, they have constant degree on A and degree 2 in X. And because of the fact that the degree on X is really only 2, and it's not too surprising that we can actually implement it using bilinear maps. And we can have a public key partially hiding functional encryption for this type of polynomial. And they have simulation security, and they have actually really good compactness. The ciphertext size only depend linearly on the input length and has nothing to do with the output length whatsoever. There is a little bit of a star here that I need to explain. A caveat is that these schemes only have correctness when the output of this polynomial H is small. Okay? And what do I mean by small means that they are polynomial in magnitude. Though the function and the polynomial magnitude is a lot smaller than the size of the modulus, which is sub-exponential. You can think of the modulus as sub-exponential large. Okay, and this exactly stems from the fact that we are using bilinear parent groups. And the intuition is that we essentially do the computation inside the exponent of the bilinear parent group. And in order to extract the output out in the clear, we can only do so if the output happen to be small. And a quick note is that if we want to get a public key partially hiding functional encryption, we actually use a slightly different assumption over the bilinear parent group. In the paper, we use the secret key version, which is also sufficient. Then that can be based on the SXDH assumption we use. Okay, so this is the first tool, which is the partially hiding functional encryption. The second tool, as mentioned, is a homomorphic encryption based on LWE. I'll quickly go over a very, very vanilla version of homomorphic encryption that's sufficient for our scheme, just for completeness. Okay? So we build it out of LWE assumption. We know that LWE postulates that if we get a public matrix A and C, which is A times S, which is a short unknown vector, and adding some noise, which are small Gaussian noises, the joint distribution of A, C is pseudorandom, that they're indistinguishable from completely random elements from ZP. Okay. From this assumption, we can immediately implement a secret key encryption scheme. And for this assumption to hold, it's important to note that, to keep in mind that at all costs, we need to make sure that the unknown S prime and the noise are hidden. If we want to hide a vector X, what we can do that are Boolean, what we can do is just to add it to the C component. And to make sure that we can separate X away from the noise E, we will just multiply the noise with 2 to make the noise even. And the LWE assumption with even noise still hold as long as the modulus is odd. And as such, we immediately get a ciphertext. The C component is the ciphertext encrypting X. And we can view the public matrix as something in the CRS or in the public key. And the secret key is the unknown as prime. One neat thing is that the ciphertext is actually rather compact, right? So the size is linear in the length of the input. And this very basic encryption scheme has only one ciphertext security. And why? Because we are kind of reusing the public matrix A, which means that the unknown as prime, which is the secret key, can only be used once per the LWE assumption. But that's enough. And it has one ciphertext security, and that's already enough for our purpose of building functional encryption for NC0. The most important property of this encryption scheme is that it has almost linear decryption. When we want to decrypt, all what we want to do is to multiply S prime with the public matrix A and subtract it away from C. And that linear operation already gives us the encrypted input X perturbed by some even noise. And now we can recover the X by doing mod 2. But the important thing is that with just a linear operation, we already get almost the encrypted input, albeit with some noise. So how do we add homomorphism to this very basic encryption scheme? Well, that basically involves looking at the almost linear decryption equation. And let's think that if we want to evaluate an NC0 function, well, that function, first of all, can be always written as a degree D polynomial in ZP. Why? Because every Boolean function with a locality D can be written as a multilinear polynomial with degree D, at most D, in any field ZP. Now we can just evaluate this polynomial f on both sides of the equation. And on the right-hand side, we see that every component, every output element can just be viewed as consisting of f of x together with some even noise, right? And we lump together all those monomials that involve at least one term of E as the new even noise E prime. And hence the right-hand side is just f of x plus 2 times some new noise E prime. The left-hand side, because function f has degree D, it can always be rewritten in a format into some matrix CF that depends on A and C. Yeah?
So let me just make sure, if you could go back for a second, I just want to make sure that I understand what you're doing. You are basically saying that because f only has constant degree, if you expanded out all the parentheses, then you will have basically f of x plus a constant number of terms that all have 2 in them and a bunch of other stuff as well. And those are not going to be too big because, or too non-sparse because there is only constant number of them.
Exactly. That's exactly what I'm saying. Yeah, here we're talking about LWE. So the exact property we want from E prime is that they're small. And I will note that again in the next slide. Thanks for mentioning that. Yeah. And on the left-hand side, basically, we can write this degree D computation on A, C multiplied with S as being the multiplication between a matrix CF that depends on A and C and all the degree D monomials in S. And we notate, like denote all the degree D monomials in S in a vector in this like tensor notation, which is sort of like you tensor this vector D times with itself, and that definitely contains all the degree D monomials in it. So the left and the right-hand side equal, and this gives us a very desirable new decryption equation, which is still almost linear. And on the right-hand side is the left-hand side, we can view this matrix CF as the homomorphic evaluation output ciphertext, which in particular has degree D in A, C, which is original ciphertext. Its dimension is rather large. We're really doing brute force expansion. So its dimension is going to be at least the secret key dimension to the D. But as long as you know we're computing constant degree function, this is really fine. This is still trackable. On the right-hand side, we still get the output perturbed by some small even noise, because this E prime is degree D in the original noise E and the input X, and both of them are very small. And we note that because it depends on X and E, at all costs, we must hide them. But the fact that it's small is going to help us to hide them. Okay, so these are the two tools that we're going to use. And let's see that when we plug them back into this framework for constructing FE for NC0, what happens, whether we solve the problem. So the idea now is that we're going to use exactly this simple homomorphic encryption, where the ciphertext is A times S prime plus 2E plus X. And the secret key can only be used once, this S prime, and the noise are going to be just sampled fresh at each encryption time. The public matrix A is going to be sampled once and contained in the master public key. Now the simple FE scheme, we're going to instantiate using this partially hiding functional encryption scheme for degree 2.5 polynomials. And it allows us to encrypt a public input, which is the homomorphic encryption ciphertext, and the secret input, and we're just going to include all degree D monomials in the secret S. Now the function H that we compute first does a homomorphic evaluation, which is to compute that big matrix CF, and then decrypt this ciphertext. Now decryption is almost linear, meaning just do multiplication with all degree D monomials in S, and that already gave us the output perturbed by some even noise. The good part is that we started with using these tools in order to make sure that the complexity of this function H is not too high. And we observed that we achieved this goal because the public part of the computation is only degree D. And the secret part of the computation is just degree 1. So obviously it's the overall, this whole thing is degree 2.5. We also note that the compactness is pretty good at the moment because the homomorphic ciphertext is linear in the input length, and all degree D monomials in the secret S, you know, it does blow up fairly big, but since the secret of the LWE is just, you know, security parameter length, so it's still security polynomial in the security parameter, and that we can tolerate.
And I hope other people can also chime in and not. I just have this all the question. Why do we think of this as 2.5 rather than 1.5? What's the kind of calculation? Like you might say, okay, it's a linear secret. So if we just say everything public is 0.5, why don't we think of it as a 1.5 degree?
Yeah, you're completely right. At the moment, it is 1.5. At the moment, it's 1.5. Yeah, I'm just doing an upper bound analysis. But later on, we will see that 2.5 is necessary. Okay, everything is great except for this bug of reveal of the noise, which is a very annoying security bug. That, as we mentioned, that at all costs, we must hide the noise because it depends on X and E. And if you think about it, even if we don't know how to exactly recover X from E prime, if we want to apply the LWE assumption, we need to make sure that E prime is hidden. Otherwise, as soon as some information about the E is revealed, I cannot apply the LWE assumption. Well, normally that in the homomorphic evaluation decryption, we get rid of E prime by doing mod 2, but that is actually a very complex computation in NC1. So we cannot stick it inside the function H. Fortunately, as we said, the saving grace is that E prime is small, it's polynomially bounded. So there is a much more efficient way of hiding it, which is just to add some larger noise to it to flood it. And the neat thing is that if the flooding noise is large enough comparing with the magnitude of E prime itself, then we know that the statistical distance between rho plus E prime and the rho is able to be bounded by 1 over lambda. Okay? So this means that E prime is partially hidden once we add rho to it. partially hidden because the statistical distance between rho plus E prime and the rho is not negligible here. It's 1 over lambda, which is normally insufficient for cryptographic purposes, but at least it's something, it's partially hidden. And why are we kind of only looking at 1 over lambda statistical distance, but rather negligible distance? Well, just whack up the magnitude of rho large enough, we can actually make the statistical distance negligible. Well, that's because of that annoying star that we had on the partially hiding FE. We can only extract the output, meaning the whole thing, 2 rho plus Y plus 2E prime, in the clear if they're polynomially bounded. Okay, so if rho is polynomially bounded, we at best can achieve some inverse polynomial statistical distance. And that's why. But nonetheless, this gives us something. So now our new purpose is to try to use H to compute Y plus 2E prime plus 2 rho with some smudge noise. The next question is, where do those rho come from? Well, we need as many rows as the length of Y. Well, one naive thought is, well, and those rows must be secret, right? If they're public, then clearly they don't hide anything. So since we need to hide it, why not just put it in the secret part of the partially hiding FE? Well, this is still satisfy the degree requirements, gives us some partial security, but it completely kills compactness because we need as many rows as the length of the output Y. And this naturally leads to the idea of using a PRG, right? When we need many randomness and we don't want to use so many true random coins, we use a PRG, right? Then if we have a PRG, we can just only encode the seed of the PRG in the secret input of the partially hiding FE. And inside the function H, we're going to first expand the PRG to get those smudge noise rho and then add it to the output. For this to work, and we really need a very simple PRG because function H is so simple. We need to keep function H simple. And this leads to our key pseudorandom object that Amit mentioned, the structure seed PRG.
Rachel, maybe small question.
Yeah.
I'm not sure that it's well defined, but you said that you have some right. The problem was that you have some leakage on the noise, right? You can smudge it partially, but you still have you still can learn some information. So okay, so you generate pseudo-random noise, but you could kind of try to, like, we have all sorts of techniques to amplify hardness or you know, to immunize encryption schemes. So couldn't you use like maybe secret sharing based tools in order to do these kind of things? Like to say, okay, I lost some entropy, but still it's okay because things are hidden?
Yeah, you're 10 steps ahead of me. That's eventually what have to happen because what I'm presenting now will at best give you partial security. So after we get a partially secure functional encryption for NC0, we will need to at some point bootstrap, amplify the security back to full before we can get IO.
Thank you.
That's a good question, yeah. Okay, but for now that let's stay satisfied, content with even just getting weakly secure functional encryption for NC0. Now, coming back, yeah.
Maybe again, like the point the response to Benny is that yes, Benny is right and you could do it, but the inverse polynomial leakage was not the reason why you had all these issues so far. The reason why you had to work so far is not to avoid the inverse polynomial leakage, but rather to get compactness.
Yes, yes. To get compactness, yeah. Or right, it's a combination of different technical limitations. Like one is that we only have partially hiding FE from bilinear maps, and then bilinear map only allow me to get small outputs out of the exponent. And the way that we handle computation is by homomorphic evaluation, and that we need to hide the noise, and we can only hide noise by adding polynomial large noise. So it's like a little bit, I don't know, I mean, hopefully there are other ways of doing it, but we're sort of really working under the constraint of different primitives. All right, so when we come back to this pseudorandom object, that a classical definition of PRG has 3 algorithms. It allows us to first sample a function index. And this function index, you can view it as all the information that is made public, right? And then it allows us to sample a seed for a particular function index. And finally, given the function index and the seed, we can evaluate the output. So we want the polynomial stretch, meaning that the length of the seed is really sublinear in the length of the output. And the PRG that we evaluate is really the evaluation algorithm with the function index coded inside. So normally that we want to make sure that given the function index, the output of the PRG is indistinguishable from a truly random string of the same length. And now, this is really, so far on the slide, this is really the most vanilla like crypto object ever, one of the most vanilla object. But we add this very non-trivial requirement on it. We want this PRG to be simple. And simplicity for us means that the evaluation algorithm for any function index I is computable by a low degree polynomial. In fact, we need a degree 2.5 polynomial. But in general, that this is an open question that people have looked at, and there had been quite an extensive line of work trying to minimize what's the degree for evaluating PRG. What is relatively on solid ground are degree constant PRGs. They can be instantiated using Goldreich PRG and NC0. And so far that now we can ask, what's the smallest constant that we can have? For degree 2, we have no good candidate, and we just want slightly stronger, slightly more complex computation of degree 2.5. And to handle degree 2.5, we have to change the syntax of the PRG slightly. Now we allow the seed to contain a public part, which is the public seed, and the secret part we call the secret seed. And the indistinguishability security now says that even given the public seed, the output of the PRG shall be pseudorandom. Now, degree 2.5 means that this evaluation can be done by a polynomial that have constant degree on public seed P and only degree 2 in the secret seed S over the Boolean cube. So at the first glance, that it's strange that why does this public seed help at all? In fact, our instinct for having something that's public is to just fix that public value, sample it well at random once and fix it and reuse it, right? Why not? We can just sort of put P, this public seed, into the function index, and then it will come back converted into just a PRG in the secret seed. Why doesn't that work? That doesn't work because that we allow the public seed and secret seed to be jointly sampled by this seed sampling algorithm, and it can be arbitrarily correlated. In fact, in the instantiation, the public seed can be viewed as an encryption of the secret seed. As such, if we fix the public seed, it's actually computationally difficult, intractable to sample the corresponding secret seed. And that's why the public seed is not reusable at all. And we should absolutely utilize this fact to instantiate such degree 2.5 PRG.
So maybe, okay, so that's maybe like a very good way. Maybe the way to think about it is really that the public seed is a function of the secret seed. In some sense, it's a, so it's more like you're leaking some partial information. So rather than maybe thinking of it as a seed, maybe it's better to think of it as a leakage. And as long as your calculation is only degree 2 in the things that are not leaked, and you're allowed to, and this thing is still secure even after the leakage, then it is then it's fine.
Yeah, you can view it that way. Then we want the leakage to not hurt the, in some sense, the pseudo-randomness of the PRG.
Right,
but somehow the expansion you're computing with respect to both the leakage and the and the seed, right? I mean, so in that sense, this interpretation as leakage is somehow, you do want to think about the seed because the expansion is with respect to the joint length, if I understand correctly from Amit's talk.
That's right.
So maybe the leakage should be also short, which is not an unusual assumption for leakage. So you want to make sure that there is a small amount of so you somehow you could say you have a pseudorandom generator and it works in 2 steps. One step could be pretty complicated, but all it does is produce some intermediate state that is then leaked out, and it's not too big, and then there is a simple computation.
Yes. Yeah. Right. And then the fact that the length of the public seed needs to count is exactly because it's not reusable, right? So every time when I generate, I'm generating 2 parts together, and then none of them is reusable, then their length has to count towards compactness. Okay, so this is the key pseudorandom object that we were built. So previous work has already had this notion embedded inside, not explicitly formalized as in JLS, but the ideas were already there. But however, they used sort of new assumptions to instantiate it. And in the new work of JLS, that we show that if we assume LPN over larger fields, we can actually convert any PRG in NC0 into a degree 2.5 PRG. Albeit that it will only have weak security. Okay, so I'm for now not telling you what is the weak security, but let's pretend that we actually really have full security structure seed PRG and come back to this paradigm to complete it. So now with this degree 2.5 PRG, what we can do is that we can now encrypt the public seed in the public part of the partially hiding FE and the secret seed in the secret part of the partially hiding FE. And the function H can now first evaluate this degree 2.5 PRG to get random bits, and then lump together the random bits to get slightly larger smudge noise, and then finally add the smudge noise to the output to hide the E prime. Because of the fact that the PRG has degree 2.5, now we see that this function H has degree 2.5. And we still have compactness as we desire, because now the length of the ciphertext increase by the size of the seed. But since the size of the seed is sublinear and the partially hiding FE has really, really good compactness, overall the size of the ciphertext is sublinear in the length of the output. Now, let me quickly walk you through the security. Security wants to say that given the public key, 1 secret key, and the ciphertext, the only thing revealed is Y. And this involves proving that for any 2 input X0 and X1, their ciphertexts remain indistinguishable given the public key and the partial decryption key. And we will only be able to prove the weak security. And we'll see that the weak security comes from 2 sources. And the weak security means that the indistinguishability, the distinguishing gap is only upper bounded by 1 over lambda instead of negligible. So starting from this distribution we care about for some particular input XB, we observe that the master public key, secret key, and the ciphertext are all belonging to the partially hiding FE. And it has a simulation security, so we can simulate these components using the output. The output computed by the partially hiding FE is exactly Y plus 2E prime plus 2 rho. And here in this distribution, rho is generated using the structure seed PRG. Then next, we can immediately use the structure seed PRG security to swap rho to truly random smudge noises. And then by the statistical arguments that we see that E prime plus rho prime is statistically close to E prime itself without E prime. Okay, so I am wrapping up. This is the last slide, yeah. Is statistically close to rho prime itself, except that we have now a distinction gap of 1 over lambda. And at this hybrid, we observe that nothing about the homomorphic encryption ciphertext is revealed, not the secret key, not the noise, nothing. and hence we can swap XB to encryption of 0. And finally, when we say that we only have weak security for the degree 2.5 PRG, we mean that the pseudorandomness achieved also has distinction gap upper bounded by 1 over lambda rather than negligible, but this does not change the statement of the lemma. And that's the end of my part. I have shown you that how we managed to get FE for NC0 with only weak security. And this, using the existing bootstrapping, give us FE for P with weak security. So we'll need one more additional step, as Benny and the boss discussed about, of security amplification from FE for P from weak to full security. Then we can get IO. Okay, and I will leave the other details, and Ayush will next to talk about construction of degree 2.5 PRG.
Thank you so much, Rachel. So any questions? Maybe maybe we can take, let's see, how does the schedule look like? Just so we have,
Rachel?
Yeah, so maybe we can take a 5-minute break, and Ayush can start in, let's say 7-minute break. So Ayush, you start at 11:30.
That's fine. Yeah, sure.
Yes.
Rachel, I have a question. Could you summarize the function that was being hidden by PHFE? So it had the decryption of the initial HE.
Yes.
And
that's this slide, I believe. Yeah. It has so the function the partial hiding does is first homomorphically evaluate the NC0 function f over homomorphic ciphertext, get the output ciphertext. Then it does the PRG expansion to get a bunch of random bits. And then it needs to get the smudge noise, right? And so from the bits to larger smudge noise, we can just kind of multiply with powers of 2 to get the right magnitude of the noise. Yep. And then finally you decrypt plus the noise, plus the smudge noise.
So the F here is basically the decryption of the HE.
Yes, it did both homomorphic evaluation of HE and the decryption, and also added the smudge noise. 3 tasks.
Right.
Okay.
Okay.
Any other questions?
Yes, please.
If there are no more questions, let's take a 5-minute break, and then if 11:30, Ayush will start. And Ayush, let's try to finish just 10 minutes after time, so we still have people still get a chance to stretch and not.
Definitely, yeah.
Sorry for going over time. Yeah,
no,
thank
no,
you very much.
That's fine. It's not that bad if we go a little bit over time. So let's see everyone in 5 minutes.